Right, our next speaker is David Ukala from, and he's going to talk to us about the potential. I can say this whole conference is about potential and how we can help to realise that potential. And now we've gone from looking at the tools and role models, etc. And now we're going to start looking at materials, the potentials of new materials and new processes. And we're going to start the second session off looking at bolt-up fibre and the potential that has to replace more traditional steel reinforcements. David.
Hello, everyone. Good morning. My name is David Ukala from the University of Nottingham, and it's an honor to be here. I want to thank the organizers for having me here. First year of a PhD program, and at the University of Nottingham, we are going through a research using basalt fiber reinforced polymers as alternative to steel for CRCP, which is the continuous reinforced concrete polymers. And I am currently being supervised by Dr. Nick Tom, who is a transportation expert, and Dr. Jeja Temou, who is in structures. And I am more of a concrete person as well, with transportation, with a little history on construction, roads, bridges, and teaching as well in the university. So thank you for having me. So a little background. I'm sure we all know what CRCP is, but just in case, CRCP is generally continuous reinforced concrete roads, and it has the advantage of having no joints somewhere in between. And because of that, it gives us an advantage over some of our other concrete road structures, and also that of asphalt. And but we know concrete with loss in moisture or temperature changes will always shrink, and we expect some cracks to take place, which therefore leads to some of the crack distresses we may encounter. And those crack distresses will lead to some crack spacing in the concrete, which will be kept regular as a result of the longitudinal reinforcement which we have embedded in the concrete. And we try to keep the crack spacing or the crack width at very tiny minima to allow for long range. However, with deterioration comes more level of distresses, mainly punch out and spalling. So punch out and spalling are main distresses we see in CRCP. And because of that, we try to design or get proper CRCP structures design to minimize or eliminate the effects of these. There are others, minimal distresses, but the typical ones we look at are the punch out and the spalling. So design processes have been established more or less to look at three critical areas. So design tends to keep our crack spacing at a range that research has shown us will be able to limit the crack the spalling and the punch out of the concrete. And different countries have or different regions have their limits. And we get a design to limit the crack spacing, also to limit the crack width to maybe about maximum of 0.6, 0.5 mm crack width. And the importance of doing that is to limit the amount of ingression of materials that could end up affecting the steel or maybe affecting the base of the CRCP. And also, we try to keep our rebar stresses somewhere between about 75% to avoid some level of maybe rupture that could take place in the member. So design processes are available for steel CRCP, and the main aim, or part of the main aim, is to ensure that you minimize the distresses which are shown in the previous slides, and also to achieve a high load transfer efficiency. If done properly, we expect that our CRCP will give us some very good advantages over other road types of, or other types of road pavement, both concrete and asphalt. We see that CRCP can last 50 years and even above. And we also have that it requires low maintenance just by the nature of the concrete being used and the nature of the reinforcement in it and the fact that it has less joints. Arguably, it also will give us better driving experience than some of the other concrete members that we have, arguably. And research has shown that it is environmentally friendly in terms of CO2, reducing CO2 emissions and reducing the fuel consumptions in our vehicles. But no matter how well designed, it also has some downsides, one of which is that, of course, we require some high initial capital, though we believe that in the long life cost will take advantage of the less maintenance it requires and maybe handling and transportation costs to have a lower cost pavement session, but you first have to bring out some capital to get the work done. And then we know that, okay, we need skilled labor for generally everything, but this we need to put skilled labor on the ground to make sure what we've designed is put on the site. And finally, we see that at a time, we expect that if things go on, research has shown that steel tends to corrode. So if it rusts, some level of debonding can take place, probably at the point of the cracks. So if it cracks and there's some alkaline or some acidic environment or carbon or what have you, we expect that this will rust. And if it's rusting the bond, it loses some bond, and we expect the crack spacing to increase, and therefore more rusting and more damage can happen to the CRCP. And more damage is not good because actually trying to get that fixed, okay, could lead to very costly maintenance, procedures. And if you want to take away the whole CRCP to replace it, maybe with asphalt road, you discover it to be a Herculean task, because while the concrete may break and can be reused, the steel, you may find it very difficult to get out of the way when you're having that problem. So basalt or FRPs, when we say FRPs, we mean non-corrosive rebars, so rebars that do not corrode. And we have fiber bars that such as glass fiber, reinforced polymer bars, and basalt fibers. They can give us an advantage to solve these two disadvantages there in terms of rusting. So our research has now shown that we don't have a design formula to currently look into the use of basalt. Currently, what we are doing is recent research has shown glass fiber bars have been used recently as a replacement for steel. However, the glass fiber bars, research is showing, they don't perform as well as the basalt bar when they are in alkaline environments, which we expect them to be in, or acidic environment if they come in contact with acidic, or even moisture if some ingression of moisture comes in contact with them while in the concrete. They don't perform well as basalt bars. So research has shown that basalt bar performs better, but currently they have been using glass bars. So we in Nottingham University are looking into the use of the design, or trying to design a basalt fiber reinforcement bar as a replacement for steel, because we believe that this is a better potential in the long run than even this glass fiber used for replacing steel. However, I'm about a few months into my research, so we have a long road to go. So currently what I'll be displaying or discussing here, we'll be looking at the crack spacing in particular. What is the potential of using BFRP? When I say BFRP, I mean the basalt bars, okay, in CRCP, okay, and I'm going to check that in 3 key areas. So first, I'm going to look at the behavior of the CRCP made with steel, the crack spacing of the CRCP made with steel. I'm going to compare existing crack models to do that. I'm also going to look at the CRCP made with, models calibrated using the glass fiber reinforcement polymer, because the glass fiber, as I said, is a bit more important. And also I will now investigate the potential of having a basalt fiber reinforced polymer in CRCP, all towards reducing or minimizing or at least managing the crack spacing of the CRCP using this non-metallic bar. So I selected we selected two popular models. We used the EC2 and also the ASH2 93 model to see what happens in the steel member when it is experienced to direct tension. And what we did was take two models that have similar kind of parameters, such as the crack space, such as the cover, the reinforcement ratio, the bar size, things like the CTE, that's the coefficient of thermal expansion of the steel, and that of the concrete, just to see what happened. Okay, other additional models exist, but for the scope of our work, we had used these two to try and explain what happens within the steel CRCP in terms of the crack spacing. And so what we did was that we compared those two models to existing literature, field literature. Okay, so Tayabji actually went and surveyed about 13 field samples and got some results. And so we remodeled it using our model, the AC2 and the ASH2 93, to see how best these models accept or how best they fit to the results that were added. And from what we could see, well, both conservative, not excellent, but we can see that to an extent, the ASH2 gave us a little bit more of something that conservatively we could work with, that could give us an idea of what is going on within the steel CRCP. So we used the ASH2 and decided to do a little more or less like sensitivity analysis to see how these members, how some of these parameters affect the performance of the CRCP. So what we did was take typical values of what we use. In the values here, the parameters here are ranging from the tensile strength of the concrete, coefficient of steel, and you see coefficient of concrete, the basalt bar, and then this X here is the crack spacing, and this P here is the reinforcement ratio, and of course the Z dash tells us the shrinkage strain. So we looked at some of these parameters and decided to take what is typically expected. We know that when we are working with CRCP, we expect to use maybe an aggregates ranging from maybe limestone to silicon river gravel, and they have a coefficient of thermal expansions as stated there. And we know that the coefficient of thermal expansion of concrete is highly influenced by the coefficient of thermal expansion of the aggregate. So we use that value there, and we did the same thing for the reinforcement. Most likely, reinforcement ratio of a CRCP, we should range between maybe 0.5 to maybe 1.2, depending, but general around 0.7, 0.65. So what we just did was to take a range of minimum typical usage to somewhere maximum that we believed was obtainable from information we got. So what we did was keep all these values at minimum. So we did, for example, using limestone, 0.55, 100 for the shrinkage, keep all the values at minimum, 1.5, 10, and put it inside here. Then when we did that, we then varied the parameter we wanted to test and see how much of an influence it was, and we varied it from the minimum to the maximum by increasing it by 10%. So we moved it from minimum to maximum to see how much, if only that parameter were to change, what will be the effect. And our results showed us that the direct tensile test, or the concrete tensile test had, if you see there, you see that as the tensile test reduced, we expected the crack spacing tend to reduce. And also the bar diameter, as the bar diameter reduced, the crack spacing also reduced. On the other hand, we saw that as the shrinkage strain reinforcement ratio and coefficient of thermal expansion, as those increased, the crack spacing increased. So it gave us sensitivity of what we expect to happen if these parameters were changed. But we could also see here between the range, for example, if you look at the direct tensile strength, well, somewhere here, okay, of the crack spacing to here gave us a wider range. So it told us that within the 200, because we changed it 10% up to 200%. So each of them. So within that 200%, it gave us a higher change, and which gave us the idea that the direct shrinkage strain was the most, the concrete tensile strength was the most influential in affecting the CRCP using the models that we had selected. And we also saw that the same for the bar diameter before the reinforcement ratio. So it went from this, and this before the other two. So what we then did was, okay, now we know how steel performs. We decided to test how does FRP bar performs. And currently, as I said, there are no real standards for basalt bar. But Bemo Crane, in collaboration with the Department of Quebec, Canada, developed something calibrated using the glass FRP. And the glass FRP, he did that, and what he just did was the same equation here for the steel was the same equation here. He just included a factor that takes into account that of the Young modulus of the FRP. So the 200 there is a 200 gigapascal Young modulus of steel, and divided by the Young modulus of the FRP. He used glass. And his model shows that this represents more of what we will get in the behavior of the FRP CRCP, okay? And all we needed to do in this case was that we just included the properties of the basalt which we had and that of the coefficient of thermal expansion of the basalt into this, and we recalibrated or redid the same sensitivity analysis as we had done before. And we compared the two results of that of steel and of that of basalt bar. And what we saw, if you see the red one is the basalt and the blue is the steel, we saw that what this tells us is that if everything kept constant, we expect double of the crack spacing if we're using basalt bar. So if we're using steel and we have a crack spacing of 1 meter, we should be expecting about 2 meters of the crack spacing. That was very clear. If only the concrete tensile strength was used, it showed us a double from the beginning to the end. So irrespective of how we increased the tensile strength of the concrete, we always had double sort of crack spacing. But we also noticed that the difference also repeated itself here in the bar, and somewhere around here it was slightly like that, and here, but we noticed that for the reinforcement ratio, as we kept increasing the reinforcement ratio, the effect of the reinforcement ratio of both steel and bars were diminishing. So you see, it started with a huge difference, and it became closer towards the end, which gives us the idea that to get the kind of crack spacing we need when we use steel, we have to increase the reinforcement ratio of the basalt bar. But the more we increase it, the less, the less the effect of it, of having a steel CRCP. And that gave us, we said, okay, if we had done what we had done before with TIABG, who did a survey test with steel with 13 sessions, we decided to test these equations, and we carried out another test another analysis using 3 different literature values we have seen by these 3 guys, or these 3 gentlemen, using the glass fiber, and basalt fiber. So we were able to get one reliable recorded basalt fiber data, and still not enough because the analysis was done for only 30 days before it was resurfaced by asphalt. But what we did was we calculated what we expected to be the crack spacing, given the values in the literature, and we compared this here, but using the steel, and we did the same using the Bemo Crane modified FRP equation. And what we see here is that the steel, this is that of the steel model, and this is what was measured by the research. And we see that what it's telling us is that it's about halfway of the basalt, which generally is what we've come to see from our sensitivity analysis to an extent. And the same thing followed using the glass fiber, and also similar thing follows in the glass fiber. However, when we use the model shown here, we saw that it actually overestimated the crack spacing which we had in the literature, but the difference was not as much. Okay, so while the data is not quite enough, because the idea or what we are working on is to develop models that actually represents this as close to as possible, but it gives us an idea that we should expect that between the model of the steel and that of this equation, our basalt behavior should be somewhere in between. And so we decided to carry out a little test to just show if this was possible or tenable, or if it was possible, and we decided to conduct a direct tensile test on 2 concrete prisms, and what with these values, and all we did was just put a bar in between the 2 concrete, 1 basalt, 1 steel, and we pulled them. We believe that the philosophy or the thinking behind it is that for steel, for the CRCP, we know that the concrete will shrink, the steel provides a resistance to it, and stresses develop and cracks occur. So in this case, we put the steel, and we expected the concrete to provide a little resistance. Stresses will develop. When the stresses are greater than the tensile stresses, cracks will occur. And we were able to get some level of transverse cracks like this. And it showed us also in the results, we were able to have about 4 cracks using the basalt section, and also about 8 cracks using the steel. So our crack spacing was much lower for the steel than the basalt, which our modeled result had shown. And when we subjected this to our 2 equations, we discovered that, again, as we have said, this is the basalt bar section, this is the steel, this is that of the basalt model. And we can see that the section fell in between the 2 as we had proposed before. Now, before I say that, so finally, we looked into looking at a range of all the possible minimum values that can be used. Okay, so what we did is the most minimum value that can give us the crack spacing in all parameters, and then we use the highest values that can give us the highest crack spacing to see a range of what we can get. And what we did, we compared that with a standard of 1 to 1.8. I think the National Highways or the AASHTO recommends something like that. And then we decided to check that of steel, and we decided to check that of basalt. So what it means that between the value here and theoretically, between a value here and a value here are all possible crack spacing for the basalt, for the steel, and for the model using this of the basalt. And for what we have seen so far, we expect our model to fall somewhere, or reality of the basalt to fall somewhere in the middle of this. That concludes or gives us that, well, we can get desired crack spacing with our basalt bars in CRCP if we can use our models or tweak our models right to give us the kind of value that we may need. So in conclusion, that is part of our conclusion. BFRP, what we are saying here is that to get a good maybe result, we should be interested in using a thin, maybe small size reinforcement bar, okay, a little higher ratio of our basalt bar to get something reliable. But then more work is being done and needs to be done to develop models like maybe what Federico has in store for us to put into this and get it working. Before I take my bow, I would like to thank Olitech for making the materials available for me. Thank you very much.
Any questions for David?
One of the items that I'm always aware of with steel reinforcement is its expansion coefficient that's very similar to concrete, and therefore they behave together very well. How does the basalt bar compare in that respect, or do you see problems?
Well, the basalt bar actually is similar to concrete. The steel is not as similar to that of the concrete. The basalt bar is lower. So what happens is that the tend to behave, the stresses tend to develop less. So what happens is that if the steel bar is having a large coefficient and the concrete having a less, you expect there to be conflict, which requires higher stresses, and that's why the cracks are smaller, because then there are more stresses and more cracks. Okay, so but the basalt bar behaves just similar to that of the concrete, so it requires more of other variables for the stresses to rise to the. So it's all about the crack spacing. Okay, I don't know. Yeah.
Any other question?
David, have you looked at the practical application of laying it as a mat for CRCP? How does it compare with laying a steel rebar?
Okay, no, we haven't gotten there quite yet. Hopefully we'll get there soon. But what we decided to do was just take a look at it first as a rebar. Then when we develop our models, we begin to see other possible alternatives and see how they perform.
How do you deal with the occasions when steel bar has to be bent? I presume you can't bend the basalt bar.
Very interesting question. Well, I should have stated at the beginning that you tend to call me David if you don't have difficult questions, but if you do have difficult questions, you call me my full name. I'm extending that fellowship to you. so yeah. So that is a challenge on its own, and we will definitely get there. But so far, what we have done is currently there are models that you can pre-order, you know, what you want to be bent as it arrives, okay, but probably not done on site. So maybe when we get there, we'll do some work there.
A final question.
Yes, please.
Would you consider looking at and trialing basalt fiber produced as a microfiber in the same way that steel fibers are, so that they can be incorporated in the mix at the batcher?
Yes, we will, because there's very good, it behaves very well. Steel fiber, yes.
The labor and the intensive laying out of the.
Yes, so that is already planned because it has very good potential in giving us even better results than what we have. Thank you.
David, thank you very much.
All right, thank you.